Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Jiadong Li with us today. Hello, Jiadong.
Hello, Frank. Thank you for having me. It's a pleasure to be here.
Well, thank you for agreeing to talk about your very awesome APJ supplement article, which we'll get to
Thank you.
a little
Mhm.
bit. Let's see. Jiadong, what's your geolocation? Where are you at?
I'm in Heidelberg, Germany, Max-Planck-Institute for Astronomy and PIA.
Cool. Very nice.
Mhm.
Let's see, and it is September 24th of 2025 as we record this. So we have gone through equinox. So is Germany sort of in its fall mode yet? Are the leaves changing colors? Or are we still kind of in?
Yes.
Oh, it is.
Yeah. Yeah.
You cool.
The mountain is very colorful, and now we have yellow leaves out there, but it's also raining a lot in the autumn.
Beautiful.
Yeah, it's very
Beautiful.
cloudy.
Oh, okay. Well, it kind of goes with it. Let's see. So I'm in Phoenix, and it does feel like we have turned the corner on summer a little bit.
Yeah.
We're still getting up into the, 38 C, something like that, but it's a
Mhm.
lot better than 45 C. So we are slowly cooling down. So it's very good.
Mhm. So it's very early morning in Phoenix, right? Now.
Yeah, it's my 7 a.m.
Okay, thank you.
But one of the things you learn when you live in the Sonoran Desert is you get up early and do whatever it is you got to
Ah.
do outside. Wait till the afternoon, you will not be outside very long. Yeah. So early to bed, early to rise. Um, yeah, and Jiadong, what do you like to do for research?
Yeah. Mhm.
What do you like to do for research?
I do binary star, basically binary stars,
Binaries.
and yes, and in my PhD I do the stellar initial mass function studies, and now I in Professor Hans Walter Rick's group. We have a very big binary group studying the binary stars from Gaia and the Sloan spectroscopic data.
Cool, cool.
Mhm.
And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Identification of 30,000 white dwarf main sequence binary candidates from Gaia DR3, BP, RP, XP, low resolution spectra. And Jiadong,
Yes.
take us away.
Yes, thank you very much. And yes, this as the hard paper is about a much improved way to answer a very fundamental question in many parts of astrophysics, the
Mhm.
binary stars. And yes, and the author, I'm the first author, and second author, Yuansen Ting is a professor in Ohio State University, and also my postdoc supervisor has Walter Riggs, and also collaborate with many very brilliant co-authors, Greg Green and David Hawk and Juan Ren,
Uh-huh.
and also members in our binary groups, Johanna and Reese.
Cool.
Yes.
Very good. It's quite the international collaboration there.
Yeah, very quite international. Germany, US, and China.
Very good.
And yes.
Cool.
And
So that's
then
a
I can, yeah.
great shout out. Great shout out. So let's go ahead and let's get into it. Let's go.
Yes. Um, fundamentally, we try to answer the question of how to identify binary stars. Getting this is very critical for everything for determining for example, the properties of a single star or understanding the entire evolution path. And now it's especially challenging question for the vast majority of them because most of the binary stars have long periods and we can't resolve them visually.
Okay.
And often their spectral lines are blended together.
Mm,
So how do you tell if you are looking at one star or two star?
right.
So that is where our work comes in. And
I'm with you.
Yes, and the game changer is Gaia.
Yeah.
Also, as mentioned in the title, the Gaia mission, most of people rarely know Gaia for its revolutionary astrometry and the photometry.
Right.
But also they give Gaia gave us almost 2 billion stars, the
Right.
whole sky. Uh, but the key of our work is, I believe, is truly transformative data set is the Gaia's spectrophotometry, which
Cool.
is BPRP spectra, also called XP spectra,
Uh-huh.
and and it's something between the spectral energy distribution (ICD) for hundreds of millions of objects of the abstracts.
Uh-huh.
Uh, so actually, my personal angle of this paper comes from a slightly different field. I'm very interested in very metal poor stars,
Okay.
and these old stars are intrinsically bluer than the metal rich ones.
Yes.
And this creates a very difficult degeneracy. If you see an M-Dwarf stars that looks a bit too blue, it is because it's too metal poor, or it's because it has a hot white dwarf companion
Right.
contributing the blue flux. And so we want to try to answer this using the Gaia data.
Nice.
Now we can go to the figure one.
Sure.
And
Okay, so we got a blue photometer, red photometer, both of them called XP, some data selection, and figure one, and here we go, CMDs. Hmm.
yes, uh, yes, this is only looking at the middle panel
Okay.
is basically extinction criteria. You can see the x-axis, the colors of the star, and the y-axis is the absolute magnitude of stars. You can see a lot of them live in between the very beautiful me sequence in the red
Uh-huh.
and the white dwarf sequence in the left. And so the binary stars live in between of them. And they also could be metal poor stars. So our goal is to can we identify the binary stars from the CMD.
Yes,
And so that is a fundamental principle of our research.
indeed.
And
I'm with you.
yes,
Good.
now we can go to figure two. And
Good.
we built an emulator or say a forward model from the CMD position to XP spectra. It's purely data driven, it's empirical,
Uh-huh.
do not rely on models. And if you're looking at the left columns,
Okay.
you can see basically um, we see the model spectra. A typical white dwarf in this system is too hot, and so is SED peaks in the blue and UV.
Right.
And it's very different from the bottom panel. It's typically a mid-sequence star,
Yeah.
and the SED peaks in the red and near infrared.
Uh-huh.
So,
Okay.
so for Gaia, when Gaia observes the pair, it sees the combined flux of the white dwarf and the mid-sequence star.
Yes.
So for the binary star, it's dominated by the M dwarf, and if you move to the shorter, it's dominated by the white dwarf. So you can see two peaks in the ICD shapes. So
Okay.
that is so this unique spectral shape cannot be replicated by any single star model, which
Right.
is the key
I think be
to
blue and
our
red. Right.
identification method.
Right.
Yes.
Okay. I'm with you.
Uh, yes. Now we can go to figure three.
Figure three. Okay, so we got an emulator, and now we will get into, well, we did some of our selections there, and figure three, and this looks like a CMD.
Yes. That's what I talked about in the previous plot. If I do this fitting for every star in the 1 kiloparsec, and you can see we have both a single star fitting and binary star fitting,
Yes.
and we can compare the chi-square. Just
Ah,
do some very simple statistics. you
Got
can see basically the red dots shown in these plots have better binary fitting than
Yeah.
the single star fitting, which meets our expectation. The binary star should live in the strait between the white dwarf and the mean sequence star
Uh-huh.
sequence.
I'm with you. Yes. Very cool.
Yes.
Uh,
And so this is the good example. We can also go to next figure.
Let me ask one question.
Uh,
Let me ask one question.
yes,
You got
of course.
a dotted blue line here. What does that dotted blue line mean?
Okay, the dotted blue lines means that when we selected the candidates and we have the decomposition of the white dwarf component and the mean sequence component,
Okay.
and if the white dwarf component live in the uh, left of the dotted line, and we can give a very confident that is a good fitting of the binary model. Otherwise, it fails the binary fitting.
Okay. Okay. Cool.
Mhm.
Thank you. Hmm. Okay.
Okay.
That's a chi-square fit. And on
Yes.
to figure 4. Looks like we're going to do some spectra here. Let's zoom out and get the whole thing.
Yes.
Okay.
Okay. Maybe we can zoom in and for top panels to see it more clear.
Okay. Let's do
Yeah,
it.
yeah, great, great. So this is a good example of our asset candidates. You can see the single star feed binaries. There's a lot of things in
Yeah.
this panel.
Yes.
Yeah. Let me introduce one by one. So the
Please.
black ones are the real Gaia's observations,
Okay.
and you can see there are two peaks. One is in the blue and one is in the red, and
Yes.
and
Yeah.
and we show the best single fit in the blue colors, and and binary model in the orange color,
Okay.
yellow color, yes. And
Yes.
there are two components in the dotted line. One is the mean sequence component, and another one is the white dwarf component.
Gotcha. I'm with
Uh,
you. Uh-huh.
yeah,
Uh-huh.
yes, and you can see the black curves is very well fitted by the binary model, but
Yes.
for the single model it fails to fit.
Yeah. This is in.
So
Yeah. Oh, yes. Very bad.
yes,
Okay.
yeah, very bad. So it's convinced us that the binary model fits better than single model, and that is the way we to identify the binary stars.
Okay. Cool. And these
Okay.
chi-squareds over here. Okay. Good.
So, based on this chi-square selection method, we can have 1,600 white dwarf mean sequence binary star candidates.
Okay.
Again, and we are not very satisfied with it because although this method gives us a very incredible high purity sample of about 1,600 system,
Yes.
and it's robust, it's physically motivated as we've seen.
Yes.
But we want to ask another question. Can we find a more complete sample, but not very good purity? We
Okay.
want to make the sample size larger. Uh,
I'm with you.
so the chi-square fit is, by its nature, is very strict. It's
Yes.
now we can scroll to section 5. Uh,
Sure.
it's we introduce a Gaussian process classifier. Okay, this figure is also good.
Purity versus completeness.
Previous one.
Previous one. Yes.
Yeah, here. Now we can, because we build a forward model,
Okay.
empirical forward model, so we can make a synthesis of the binary stars.
Okay.
Given a white dwarf and the mean sequence star, we can uh, synthesis the binary stars XP spectra, and then we can introduce
Cool.
the machine learning method. Here we use the Gaussian process classifier to train a GPC. This is a very powerful and flexible machine learning technique.
Uh-huh.
Yeah, so instead of fitting a XP forward model, we are going to teach the GPC algorithm to recognize the pattern
Yes.
of a white dwarf mean sequence binary directly from the spectra.
Nice. Beautiful.
So yeah. So the first and the most important step is creating a high quality training data set. And
Yep.
this figure shows how do we build a training data set. The red dots here are the training binary sample.
Okay.
And the gray backgrounds are the training single sample.
Yes.
So we can mark them and train the GPC. And once the GPC is trained, and we can use it to entire parent sample of the millions of stars. And for each of the star,
Nice.
the classifier can output a probability
Yes.
from 0 to 1.
Okay. Good. I'm with you. Mm-hmm.
Okay.
Good.
And so we can go to figure 8.
Figure 8. And
Yes.
these are the classifications. Okay.
Yes, here is it is. Here is the classification. It shows the distribution of the probabilities grouped into different probability bins. And
Uh-huh.
you can see from the left to right is probability go from lower to higher for the binary classification.
Uh-huh.
And you can see exactly that is what we hope for.
Wow.
And you can see there's a massive pile up of objects at the probability of 0. There are single stars in the left.
Right.
And you can see for the
Wow.
most red panel, the binary stars live in the very, how to say, in the between of the clumps between the mean sequence and the white dwarf sequence.
I'm
And
with
that is what our
Uh-huh.
expectations.
Very cool.
So the basic results of the GPC has dramatically increased our sample size from 1,600 to 30,000 candidates.
Okay.
But this is a point where we must say extremely critical of our own method as a machine learning classifier. No matter how well it's trained, we need to find a good interpretability
Yes.
in fact pattern, but are there real or some fake, some stupid thing? How can we make sure these 30,000 new candidates are the true white dwarf mean sequence binary stars?
Yes.
To answer this, we need an independent test.
Okay.
That's
Mhm.
a piece of evidence that's from the Gaia's P spectra. We can go to the next figure, figure 10.
Figure 10. Let's slide on
Yes.
down. 9, 2, 9, and 10. Okay, here's some
Here it is.
comparisons. Oh, nice. Uh-huh.
Yeah, so this figure is the
Uh-huh.
validation plot in the paper. So the core idea is very simple. Is if our new candidates is truly the binary stars and it contain a hot white dwarf, they must be bright in the UV bands.
Yes.
So we cross-match the Gaia to the Galaxy. It's a satellite that gave us the UV photometry of all sky. And if we have the UV data, we can independently to confirm us that the GPC method did find the white dwarf mean sequence binary stars.
Right.
And the normal mean sequence stars are cool and incredible faint in the UV.
Uh-huh.
So UV detection, sorry?
Yeah, I'm good.
Okay. So the UV detection, again, the UV detection is a smoking gun signature of a hot containment.
Right.
And for this, and in this figure, I show the color magnitude diagram in the UV colors, and the middle panel is NUV minus Gaia's BP colors, and the red panel is far UV minus BP colors.
Cool.
Let's break down these 3 panels. In all of them, the gray points are single stars.
Yes.
And the blue circles are the original high purity sample from the cat-square fitting I mentioned before.
Correct. Correct.
And the red circles are the new candidates
Nice.
found from the GPC method. And so the red circles are the one that we need to validate.
Right.
And so on the left, this is our familiar Gaia CMD. This is just, you can see for the red ones, you can hard to tell whether the red dots are the white dwarf mean sequence binary because they are overlap with the mean sequence. Many of them overlap with the mean sequence.
Yes, they do.
Yes.
Uh-huh.
But on the middle, we show the UV colors. You can see the red dots move to the left to the mean sequence. So that is very fast. That's very, very good.
Yes.
And the single stars, the gray points you can see in the middle panel, basically they're all clustered on the red side. So they are UV faint as our expect.
Yes.
You can see our good standard cat-square sample, the blue circles are all located far from the left.
Yes.
And the GPC sample living in the between of them, which confirms that they contain the hot white dwarf stars.
Cool.
So, yes, so that is a very independent validation.
Yes, it is. Very good.
Yes.
Very good.
Yes. Now we can go to the discussion part. We do some. Maybe here, the table. We can leave the table for a second.
Okay, hold on one sec. Let me find it. Is table 3?
Table 3.
Okay.
Okay. So we just want to make sure because there are a lot of sample production in this paper. I want to make sure. So cat-square is the high purity sample. Basically, on the cat-square selection shows they are of the highest purity.
Yes.
We have 1,700 of them. And the GPC sample is the QC sample I mentioned before. We have 55,000. And we do some quality costs. We have 30,000 of them. That is a number in the title and also the abstract. Yes.
Yeah.
Yeah, I want to make everything to be clear.
Good.
So now we can go to the next figure.
Okay. So
discussion part.
Cuts and figure 11.
Yes.
Okay.
Here I show the comparison of the previous literature, both Lamos and Sloan white dwarf mean sequence binary stars. And you can see after we cross-match them, basically they agree with, our results agree with the both Lamos and the Sloan white dwarf mean sequence binary stars.
Very good. Okay.
Yes. And the red panel shows the cat-square. You can see basically most of them favors a binary fitting of the Lamos and the Sloan binaries.
Gotcha.
And also have very high probability of being a binary star.
Yes. Okay. Good.
Now we can go. Yeah. Now we can go to the discussion part.
Okay. Let's see. Figure.
Yes.
I think
figure 12.
We started with. Let me just slide up. So the discussion's section 5, yeah.
Yeah, section 5. Yes. And so now we want to do some basic statistics of the binary sample we selected. The cat-square sample. Why the cat-square sample? A major advantage of them is that our fitting approach is that we can derive the physical parameters of both components.
Yes.
So we know everything of the binary stars.
Yes. I'm with you.
Yes. Now we can go to figure 12.
Let's go down to figure 12. There's what's our selections, comparison with existing literature, and here we go. Comparison to stellar masses. Ooh, very good.
Yeah, here we go. Yes, this one.
Uh-huh.
And
Uh-huh. Uh-huh.
we see the properties of the Mie sequence. No, we can see the properties of the field white dwarf. Here is the white dwarf stellar mass of the white dwarf distribution,
Uh-huh.
and the blue curves are from literatures
Yes.
shows the white dwarf stellar mass of the white dwarfs in the 100 parsec nearby solar neighborhood.
Cool.
You
Yes.
can see basically they peak at 0.6 solar mass.
Yes.
And for our chi-square binary stars, you can see they if we uh, if we derive the stellar mass of their white dwarf companion, we can see a different peak at
Yep.
0.4
Thereabouts.
solar mass.
Mm-hmm.
Yes.
Mm-hmm.
So that is maybe uh, some physical reason behind that. The fact that our method, which knows nothing about white dwarf physics as a prior, so I think our white dwarf stellar mass, stellar mass distribution has no critical selection effect. If that is true, can give us confidence that the distribution of the binary stars are different from the single stars.
There you go. Yep. Mm-hmm.
Yes.
Mm-hmm. Interesting. Very interesting. Okay.
Yes. Now, I think that's covered the main pages of the paper.
Okay. Very cool.
Mm.
And
And
there's a couple.
I'm ready to go back to any figures and discuss any part of the method in more detail
Okay.
if you have any questions.
No, I just want to alert people that there's also a very awesome four appendices that one should check out. It's got another figure and some 25 equations detailing a little bit the method. So do check that out. Do check that out. No, that was uh, Jiadong, that was absolutely wonderful. So thank you so much
Thank you.
for walking us through your very awesome APJ supplement article. Very nice.
Thank you very much.
Sure. Let's see. And you kind of touched on it there a little bit at points, and so let me go ahead and push on a
Sure.
couple of points. And where do you think we go from here, given the published article? Is there additional maybe high resolution spectra that one might want to do?
Yeah. I
So,
forgot.
so,
Sorry.
no, that's why we're here. This is where we cover the future, right? So where do
Sorry.
you think we go from here, given
Yeah.
the published article?
Mhm. We can go high resolution follow-ups. Yeah.
Yeah. Okay.
Mhm.
Okay. Is there additional machine learning models that one might want to try on other than chi-square or Gaussian process?
I think that would be fine. I think the chi-square, both chi-square and the GPC, I think is the method that's state of the art. Okay, I don't want to try another method, so I would say this the follow-ups, high resolution follow-ups.
Okay. Very good. Good. So tax. Let's give him some time to do something. Very cool.
Okay,
Very cool. Dong, I want to thank you so much for walking us through your very awesome article. Very nice. Thank you.
thank you very much.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye bye. Thank you.